Hello, I'm David. I'm coordinator of the Maths Learning Centre here at the Uni of Adelaide. It's semester 1, 2025, and this is a revision seminar for differential equations. As I said yesterday, last one for this version of the course. So there you go. Fun times. Okay. Okay. So I've had several requests, and we're going to start off with existence and uniqueness. If you're watching this video in the future, there will be on YouTube or on the Maths Learning Centre's website a list of what I talk about and what time minute mark it starts, so that you can skip to the bit you want. Okay, well, the people call it existence and uniqueness, but it's existence and uniqueness of solutions to initial value problems. That's what. So we're talking about things that exist and things that are unique. The things that exist and might be unique are solutions to initial value problems. That's what it's referring to, according to the notes. Actually, do you know what? I should just share my entire screen so that I can switch between windows without having to mess around with things. So these are the notes written by a sequence of various maths lecturers at the Uni of Adelaide. The front page has all of the authors. So they're not mine, just for copyright purposes. They belong to someone else. The most recent person who has made changes is Michael Chen, I believe. And this is the theorem. And it says that, and I'm going to copy it down while I say it. And let's see. It says, consider the IVP, that stands for initial value problem. Y dashed is some function of x and y, and y of position x0 gives me result y0. Okay. So before I continue, I just want to make sure I understand what this means. This means my differential equation is written in the format dy on dx equals some function of x and or y. So any other form of writing a differential equation does not match with this theorem. So if it's got a y double dashed, nope, doesn't match with this theorem. And if it's got stuff multiplied by, if it's got a y dashed squared, like you're going to have to get it to the point where it's y dashed equals before you can use this theorem. Now that's the first thing I've noticed about the way it's written. Okay. And I say here x, y, when I read it aloud, that's x and or y. It might not be a function of any of those things. Could be a constant. That's fine. It doesn't have to involve both x and y, but it generally does. It is very common in differential equations for it to only involve y and to not have any x's at all. That's an option as well. So yeah. Okay, so if in some rectangle, okay. So this is the rectangle people were referring to earlier. This rectangle is called R. Okay. And it is the set of points x, y, such that the distance between x and x naught is less than a, and the distance between y and y naught is less than b. Okay, so the next thing to understand is that. And so that rectangle would be something like, there's x naught, y naught. And it says that the distance between x and x naught is less than a, so I can go a either way from x naught, and I can go b either way from y naught, and then that's the rectangle. Okay, that is the rectangle R. Though technically the edges are dotted because it's a less than sign. It doesn't include the edges itself. It's an open set. That's, I'll just do that. I don't know if that's very important about it being an open set, but like if you ever do real analysis in the future, open sets are like a whole thing. So real analysis is about the theory of differentiation. So it seems reasonable that it should be an open set. I know that because, you know, I help with real analysis too, as well. So yeah, okay, cool. So if in some rectangle something happens, what happens in this rectangle? The function fxy is continuous and bounded. Okay, so that's a multivariable function there. So it has to be continuous in the multivariable sense, meaning that if you approach any particular point from any direction in the plane, you'll get the answer will always approach the same thing. That's more or less what continuous means. But most of the time in this course, you can just look at it and go, oh, well, the denominator is not zero, and that's fine. So yep, continuous and bounded. And oh, they've given me a meaning for bounded, which is that the absolute value of f of x, y is less than some number k. Well, that's what bounded means. Bounded means it doesn't go up or down forever. So there must be a limit to how high or low it gets, which is what this k is. Okay. So if all of this happens, then, okay, so there needs to be a rectangle where it's continuous and bounded. Okay. So I'm imagining here that there's like a 2D function, this height, which is what f of x, y is, because that's what this is. And it goes up and down from here. You don't normally think about it that way, but that's what it's saying. Okay. But it's also f of x, y is in fact y dash, which is the slope. So it's saying the slope is bounded. So the slope of the function that we're trying to imagine passes through this point it's never infinity. It's inside this box, it gets to a certain steepness and then stops. It doesn't get any steeper anywhere else in here. So, okay, cool. Then, oh, and it goes to the next page. It's such a, it's like one of those TV shows. It's a cliffhanger. That's the word for it. I just couldn't remember it. Then the IVP has at least one solution. And the solution to a differential equation is a formula for what y is in terms of x, more or less. Okay. Oh no, at least one solution for less than the minimum of a and b divided by k. Cool. Okay. Cool. Sure. Huh. So in this box here, centered on x naught, y naught, maybe there's we may not know what the slope is at the maximum is at. So it's saying that no matter where you are in this box, the slope is at most k. That's what this says here. And so if I drew one of slope k at this spot, then this height is b. So this would have to be b on k here because that's what the slope is. Because every distance across is k, distance up is k times distance across. Oh, okay. And so that's saying there that actually my function may only be defined in this zone, where x is in this zone here between minus b on k and plus b on k, which is what this is. Oh, sorry. But if the slope was really shallow, that wouldn't make a difference because we don't get all the way up to height b, so it doesn't matter. Okay. Right. So the details there are bothering me, but the vibe is okay. It's saying that, look, if there's a rectangle where it's continuous, then there will be a rectangle somewhere where the function exists. It just might be smaller than the one I first thought of. So even though fxy is continuous here, and I would like to draw my graph of my f of xy through this point, it may not I may not be able to continue it all the way to the edge of the box. It may have to stop somewhere. Okay. Cool, cool, cool. And then so that's the existence part. So this part's existence. Because it says there's at least one. So that's saying that a solution exists. All right, and then there must be a bit about there being only one solution. So further, oh, okay, further, if also f, so that's the y derivative of this thing is continuous and bounded as well. Yeah. In the rectangle R, then, oh, and it has, yes, because it's bounded, it's got a bound as well. Cool, cool, cool. Yep. Then the IVP has a unique solution in that same zone. Okay. All right. And this says the word unique, so it's obviously the uniqueness bit. Right. So it seems to me that there are questions that you should ask about this right from the start. We've already asked some. So what does the rectangle mean? We've asked what does bounded mean? And we've asked why this minimum, I can turn that off and come back to here. We've asked why this minimum of A and B on K. But I think the big question that I would be asking is, why do we care? And I think that's because most differential equations that people have been interested in over the centuries are of the form, I can write the derivative in terms of the current value of x and y, and I would like to figure out a formula for what y is in terms of x based on it starting at a particular spot. And usually the x is time. That's why it's called an initial value problem. And usually x0 is time is 0. And like when you did Euler's method in Maths 1B and probably again in this course, what Euler's method is that Euler's method is designed for differential equations like this. So I'm just going to make a connection here. For this situation, that also appears in Euler's method. So Euler's method is a way of not solving the differential equation, but just giving you a specific number answer for a specific x. But this theorem will help you feel better about the fact that you didn't solve it because you know there was only one solution anyway. And so if you happen to just find one y that goes with the x you're thinking of, then you can be sure that it is the y that you want, or at least nearby, because you know there's only one because of the existence and uniqueness theorem. I think that's one of the reasons why we have it. But Euler's method is designed to start at a particular spot, and you know what the slope is at any moment. So if your function passes through a particular point, then this formula will tell you what the slope of the function is at that point. That's what this says. And so it's intense. You know what the slope is here. And if you follow that slope for a bit, you'll get to a new point, and you know what the slope is there too, because there's a function for it. And you follow that slope for a bit, and you know what the slope is there too. And so you follow that, and you do this idea. And you keep following the slope from the point you're up to. And if you did that perfectly smoothly and did it some teeny tiny distances, you should be able to get whatever the graph actually does. And you should be able to follow it backwards just as well. And so this is the goal. We are trying to find a graph of a function that passes through the point we're interested in based on the fact that we know what the slope is at any moment if the graph passes through that point. That's what we're trying to do. And the existence and uniqueness theorem says that there's a limit to how far away from that you can be sure that there is an answer. And you can only go as far away as this function being continuous and bounded. That's as far away as you can go and be sure that there is an answer at all. You need the derivative of that with respect to y to also be continuous and bounded, and then you can go a certain way and be sure there's only one solution. And that means that if you do Euler's method, you can go, okay, so well, since the boundedness of this thing, I need to have and I want to know it at this point, I need to have my starting point close enough to that to be able to be sure that there's an answer. That's kind of the idea, I think. Does that help at all? I don't know. I've never said it that way before, and I like it. Okay, so then that's great, and you understand the vibe, but then you get given a question, and it's a whole different thing. And so we should talk about that too. I don't know. I'm just going to make one up. It's going to be awful, but it's okay. We'll survive. And I will choose that y of half is 1. I'm just making up a question that may turn into horrible, horrible stuff, but it's just worth a try. And if we can make sense of this one, we can make sense of anything. So, and I don't want something that's already in the course, because that means you can go and compare what I've done to the stuff in the course. So, okay. So the theorem says that I need a rectangle where this function is continuous and bounded. And so I'm just going to draw an x, y, and here we have the point half 1. Okay. And then I know that y dashed is undefined when x is plus or minus 1. That's the first thing I'm going to think of. So I know that I'm going to give this function a name. And if you got a raw differential equation, it'll never say f of x anywhere. You have to declare that this bit is called f of x. So f of x is equal to this, and it's not continuous when x squared minus 1 is 0, because the denominator is not allowed to be 0. That's ridiculous. And so I get x squared is 1, and so x is plus or minus 1. So it's not continuous at those points. And it's not bounded in any region that contains one of those places on the edge. Because if you get really close to x equals 1, the denominator will be really close to 0. And if you divide by a number that's really close to 0, you get a really huge answer. And so I can't go all the way up to 1 or minus 1. So I'm going to add that to my graph. And just for the purposes of making it obvious to the person reading this later what happened, I'm going to draw a new one. And so there's 1, and over here is minus 1. And when x is 1, the function is not continuous there. And when x is minus 1, the function is not continuous there. So my rectangle that I'm interested in cannot pass these lines, because the function is not continuous in those spots. Yep, my a value is at most a half. technically it can't be exactly a half because I can't go all the way up to 1 because that would make it unbounded. So my rectangle can only be this wide. It can only go this far. So definitely my rectangle is not going to cover any of the negative bits of x. Okay. So, but theoretically it could be as tall as I want because there's no y values that stop it being continuous. So I could make my rectangle as high as I like. But it can only be this wide. So my a or x minus a half is less than a. Has to be less than a half or I'm going to cross that point. Yes, it will have to be less than a half or it will include points where fxy isn't continuous. Okay. It can't actually be equal to 1 either, or it will include, or it won't be bounded. Yeah. So, well, that at least gets me the point there. So I know that the widest possible region where there could be a unique solution is from 0 to 1 on the x value. That's the widest it could possibly be, and it definitely can't go all the way to 1. And I am almost certain as well that because there's no limit to how high y could get, I can probably go all the way to the edge because there's no b divided by k because the b can be as big as I want. So that's my guess, but it all depends on how k interacts with that. That's a bit confusing. So I'm not quite sure what to do. I haven't given myself a question. I just wanted to think about what to do here. So if someone told me a rectangle and then asked what is the region around which where there would be a unique solution, maybe do that. Let's just add extra. If the rectangle is like x minus a half is less than a quarter and y minus a half is less than 2, just making up a random rectangle. Yes, y minus 1. Thank you. I should be using the actual y value that's involved here. And I should have given myself more space, shouldn't I? That's okay. So it's going to be go up. It's going to be a quarter wide in each direction and 2 high in each direction. So that's my rectangle there. Bad diagram because it's not to scale. So if it's that rectangle, then we could make a guess at how things work. So in that rectangle, this definitely is bounded because it doesn't butt up against this x equals 1 point. So and we would need to figure out what the bound is to know how wide we can go. And so yeah, damn. If I had a computer, I would go to the Desmos 3D calculator and just draw a picture of this. Yeah. But, well, I could. I've got one right here. But I won't if I was in an exam. So I'm just going to ponder this and think, okay, so this will get bigger the closer to x squared minus 1, the closer x squared minus 1 is to 0. So this larger for x closer to closer to 0, so that means x closer to 1. And it would be also bigger when x is bigger, because the numerator would be bigger. So that's from the denominator. And from the numerator, larger for x being bigger, but that's all right. That's already covered by x being closer to 1, so that's great. Awesome. And it's larger for y bigger as well, but for y further from 0. So when I say larger, I mean further away from 0. That's what I'm interested in. Okay, so it seems to me that the highest value should occur here, because that's where x is the biggest and where y is the biggest. And I've already indicated that this will get bigger as y gets bigger, it'll get bigger as x gets bigger, so that must be where the biggest value of the function is. That was 3/4 3. Okay. And so therefore the max is 3/4 times 3 squared over 3/4 squared minus 1. Well, don't do that to yourself, David. I really thought there'd be room to just calculate it, but the 3/4 is throwing me off. Okay, well, I've got 3/4 times 9 over 9/16 minus 1. And if I multiply top and bottom by 16, that'll give me 4 times 3 times 9 over 9 minus 16. Why is that a negative number, David? Ah, that's all right. We'll just do the maximum absolute value. Cool. And so that will be, that's 7. All right, there you go. That's what it is. Whatever that number is. It's in sevenths. It's great. I'm going to feel bad if I'm doing it. That's 12 times 9, which is 108. Okay, which is just for the purposes of this. 7 goes into 10 once with 3 left over, 15 and a bit. Once with 3 left over, and then 5 with also 3 left over. So it's going to be 5 repeater. No, it's not going to be 5 repeater. That doesn't make sense for sevenths. Oh no, 30, right, and then with 4 and then so on. Okay, cool. Which is so wider than x is, like that, you know. So that's what k is. So let's do my k as 16, that's good enough. And so therefore my unique, well, my existing solution exists for the x minus half being less than both the minimum of 1/4 and 16, and it's b on k, isn't it? 2 on 16, which is actually turns out to be narrower than we expected. So that's the minimum of 1/4 and 1/8. So it's actually 1/8. We did get it narrower after all. Wow, I did not expect that. Cool. So x is less than 1/8. Wow. So that means that x is between kind of like 5/8 and 3/8. Because a half is 4/8. Huh. I didn't expect that to happen at all. That's cool. I do want to just check something, just in that original theorem. It said here that this is less than m here. I just want to check that it didn't actually use m anywhere else, because it just seems weird to mention m without using it. Nope. They mention m without using it. Okay, cool. Sweet. Just wanted to check. Felt a bit weird. I should probably just finish that off with the uniqueness stuff, shouldn't I? But before I do, how are people feeling about what happened there? Cool. I'm very much hoping that your lecturer, if they give you one of these, makes the function easy enough to tell where the maximum is, just like that one turned out to be. Where you can say, oh, well, it increases when y does and when x does, so cool, it must be over here. That I'm hoping they do that for you, or they just don't give you one at all. That'd be great. But you can only hope so many of those things about an exam, that they don't give you one of those. There's one. I'm happy with this one problem, and just one big one of those. That'd be great. Yeah. Oh dear. Exams are evil. Some people say they're a necessary evil, but you know, they're definitely an evil. Whether they're necessary or not is a whole other question. Okay. So then I'm just going to figure out what Fy is. I just need to copy my original one. There it is. And so Fy, Xy. Oh, that's nice because there's no y's on the bottom. I don't have to use the quotient rule. That's great. Yes, I made it that way. I did that so that I didn't have to worry about what the y's were doing to find my my discontinuities. So x squared minus 1 is a constant divided, and so it will still be there afterwards. This x is a constant multiplied on, so it will still be there afterwards. And the derivative of y squared is 2y. Great. Very easy. Yay, me. Thank you, past me. Any ever read Monuments by Wilka Starkus? He's an Australian author. It's a good one. It's got time travel in it. So that's what I was thinking. Yay, past me. Because there's these scenes where this guy gives himself notes from the anyway. He's a university lecturer as well, so it's funny. So anyway, history lecturer, of course. That one, I need to figure out where its maximum, whether it's continuous and bounded inside this rectangle, which it is. Because we knew it was continuous inside that rectangle. Continuous and bounded. Since it doesn't butt up all the way against the one, it's definitely bounded. And the x's and the y's themselves are bounded, so this is going to be bounded too. So that's great. And so therefore, the solution for x minus a half is less than an 8 is unique. Right. So if it turned out that this one had new discontinuities or became unbounded, then you may have to make the rectangle even smaller to get a unique solution. But most questions that lecturers think of off the top of their head while they're planning exams are going to be very difficult to set up this new derivative thing to change the boundedness of it. Unless there was a y on the bottom, that would cause problems, I think, probably. But I maybe, well, I don't know. That's a question for another day. Feel free to ponder that. Yes. The bound the line. Yeah. What if we get written? I would decide on bounds if it's not given by. Yeah, that's a great question. So I will say, I'm going to say, how do you figure out the range for y if you don't have existing bounds and you have to make it yourself to get the continuity? Because I've seen questions where there's like an infinite rectangle and then just say, well, and therefore, of course, this, right? Well, I'm wondering what would have happened if I had changed? I don't know, but I wonder this. This is what I wonder. What if it was y minus 1 is less than b? That one there. You can close it if you want. I don't know. Close it, see what happens. Oh no, that's not the econ. Oh, it might be. But usually that button only turns it on. See what happens. Okay. Well done. Problem solving. See, they should give you extra marks just for that. What if it was that? Then what would have happened? The maximum would still have been in that top right corner, right? And so it would have been that the absolute value of x, f, y would be still at 3/4 for x. Yep. And that would have, I would do the same trick, but I'm not going to be able to do it off the top of my head. Oh, it was a -1, wasn't it? So I'm still going to get my 4 times 3 times b squared over 7. All right. I'm just skipping a bit of working, just trying to follow what I did last time. Okay. Which is approximately whatever it is. But theoretically, if I made that b tall enough, this would be beyond 1. Yeah? So if b is large enough, this is greater than 1/2, and that's the widest I can get. No, wait. Crap. Ignore that completely. The taller that is, the higher k gets, and so the narrower it becomes, right? Well, what the hell? Oh, but they'd get a point. There would be a point low enough where this, okay, wait. So we'll call this k. Yeah. I knew I'd get there. Wait. Where's mine? That's k there. And so we can do that the solution for x minus 1/2 is less than b on k, like the minimum of b on k and 1/4, just keeping the same x's that we had before. Sorry? Oh, well, it doesn't matter which order the minimum's in, because, yeah, the minimum will be the minimum no matter what order they're in. But you're right, in the traditional one, you have a first. But that I didn't think of it that way. It's much the same as when I play board games and it says you should go to the right. I don't know what left and right are. I just go whichever one makes the most sense to me on the day. Okay. And what we therefore want, if we want the full width, then we kind of want b on k to be more than 1/4. That's what we want. Okay, which means b would be more than k on 4, which is 4 times 3 times b squared on 7 on 4. Okay. B's definitely a positive number, so I can divide both sides by b. Yeah, so there is one. Oh, okay. So I have to choose my b to be less than 7/3. And then I'll be able to use the whole width. All right. I don't know if that's what the kind of thing they want, but that will do. So if I choose b to be that, then I'll be able to use the full width up to 1/4. And to be fair, I should be able to do this for any a all the way up to 1/2. So I could fiddle this out and put 1/2 in this spot and get 7/6. Okay. That's really puzzling. There you go. So I can imagine a function that may have its maximum in the middle. So if you had a function that had its maximum when y was closer to the center point, then you could probably make it as tall as you wanted, because then the k wouldn't change depending on how far out you went. Yeah. So it looks like my rectangle, I'm going to choose R to be xy such that x minus 1/2 is less than 1/4 and y minus 1 is less than 7/3. And then I'll be able to use, and then unique solution exists for x minus 1/2 is less than 1/4. That allows me to get the widest possible x if I restrict my y's to that domain. I'm puzzled by that. That's okay. Yeah. I feel like for an exam, it would be much easier if they just give you the rectangle. Or they would have asked the original question, which is what's the maximum A you could use? And we knew that right from the beginning. You go, well, the maximum A I could use is 1. No, sorry, is 1/2. It's like, yay, that's it. Because it butts up against one of the places where it's discontinuous. And they could totally give you a denominator that's got both x and y in it, and then you'll get the maximum rectangle is butts up against one on the y-axis and on the x-axis, something like that. So, okay. Do people feel better at all? Okay, good. That's I have not done harm, so that's a good sign. I've satisfied the educational Hippocratic oath, and I will continue on that point. Um, okay. Well, I did get. Well, I can talk about Fourier. There's no clock here. What's going on? Okay, we've still got an hour. Okay, and a little bit extra because the next one doesn't start till 1/2 past, but I do have to get to a different lecture theatre. Okay, water. Um, when you say Fourier series, what do you mean? What's bothering you? Okay, so just going to say that like processes to get probably coefficients. Yeah, and how do you know if you're going to have like a cos one or a sine one or both one? Is that the idea? Yeah. Okay. Oh, okay. So we're saying that there's waves, and apparently when you have the wave, you can just make a decision. Okay. All right, here we go. We're just gonna. Ah, okay. Pardon me. But they did turn up when did you guys do PDEs with separation of variables? And they turn up then, right? Okay. Um, mm, I'm just going to give us a quick scroll. Oh, and now we're in a whole separate chapter, and then they come back again later. Okay, gotcha. So then the next time they appear is back in PDEs. Just give me a second. Representing them by Fourier series. It's been like 2 pages, and then suddenly they come back down here in the okay. Yeah, but like oh. Oh no, this is Fourier series and friends, where we don't necessarily use cos and sine. Oh, and we use the complex ones. Fun, fun, fun. Uh, okay. Well, cool. I can see why there would be feelings. All right, I'm just going to talk about it for a bit and come up with questions as we go. So I don't think I've ever talked about it in the revision seminars for this course. I talked about it in the engineering one. So kind of, I might possibly have a slightly different perspective on Fourier series to the lecturer, or no, Elizabeth is not the person who wrote the notes. And so she might have a different perspective than Michael and Tony and all of those people. So here's another one. Like there's two kind of things that Fourier series are, and one of them is a series where you're trying to not that different from a power series in the sense that you're trying to write your function as a sum of a whole lot of bits. So if you've got a function, then you can write it as, a naught times this thing and a1 times this thing and a2 times that's the general vibe of all series representations of things. And usually the hope is that each of these things is smaller in some sense. Doesn't always work for Fourier series though, or that the coefficients get smaller as you go out. And so, because if you're going to add up infinitely many things, you really need each one of them to be smaller than the one before, or it's not going to add up to anything. And so with a n's getting smaller. Sometimes you can get sometimes an's or the things getting smaller as well. So if you have an ordinary power series, so this is just a generic series. If you have an ordinary power series, then it's got like 1 and then x squared and then x cubed and whatever. And if x is close to 1, like close to 0, then x to the 5 is really small. And so it doesn't really matter what the coefficients are doing because the x's get smaller, like the powers get smaller. But with sine and cos, so in a Fourier series, it'll be something like a naught plus a1 cos x plus a2 cos of 2x and so on, right? And there's probably going to be sines as well if you really want to be and the thing about cos 2x is it runs twice as fast as cos does. And so this might fit 1 period in the space of 2 pi, but this fits 2 periods in the space of 2 pi. And cos 3x fits 3 periods in the space of 3 pi. So if you think of like cos 100x, it's just going to go like this. And so that's kind of not smaller. That's annoying, more annoying. So you really need the coefficients to get smaller for this to work. Okay, so that's one of the ideas. And you need coefficients to get smaller or be mostly zero. That's what you hope for. Okay. And at the very end of the course, they went, well, a good choice for what goes in these brackets here are functions that are orthogonal in some way. So a really good, I mean, it doesn't have to be orthogonal, but a really good choice for what goes in these spots is orthogonal functions. Even better, orthonormal, but we can worry about that later. Orthogonal functions is good enough. And orthogonal functions are ones whose dot product is zero. Okay, but we'll get to that. Kneeling there. Okay, so that's that, and we're going to get to that. And this is a good choice. I'm going to write that down. A good choice, like sine and cos, are good choices because they're orthogonal in a new fancy meaning of orthogonal that you haven't been using up until now. Up until now, orthogonal has been only used for vectors. But because of the magic of abstract algebra, we can pretend that functions are vectors. Yeah. Yay. So I'm going to come back to that. My first instinct of what Fourier series are is like uber trig identities. So when you have something like this, cos of 2x, right? No, not that at all. So watch this. So cos x squared is a perfectly good periodic function. It looks like this. So cos looks like that. So cos squared, that's where cos is. And cos squared looks like that. It's a perfectly good periodic function. The philosophy of Fourier series is that all periodic functions should be able to be written in terms of sine and cos, but just with different coefficients next to the x. And I can do this with trig identities. So I know that cos of 2x is cos x squared minus sine x squared, damn it, which is, and that's two lots of cos x squared minus 1. And so what that means is that two lots of cos x squared is 1 plus cos of 2x. And so cos x squared is a half plus a half of cos 2x. Now, this is what we did back in the day when we were doing trig identities, when we first learned them. What this is saying is that there's my half, and there's cos 2x, which is running twice as fast as cos x. And it's only half of cos 2x because it only goes up and down half instead of up and down 1. So this graph really is a cos curve. But look, this is a Fourier series. My coefficient A0 is a half, and my coefficient A2 is also a half. And the coefficient A1 is 0. If we don't have any just cos of x's. And the coefficient A3 is 0 since we don't have any cos 3x's. And the coefficient B1 is 0 since we don't have any sine x's, and so on. This is a Fourier series. And in fact, lots of things have Fourier series via trig identities. If you have a function that's periodic because it's made out of trig functions, then you can write it always in terms of a constant plus some cos of something x's and cosine of something x's, always. That's how it works. That's what trig functions, trig identities mean. So for example, if I had like cos of 3x, sine of 2x, I can rewrite that as just something cos of x, something cos of something x plus something cos of sine of something else. I can do that if I want. And you don't have to know how to do this, but I just wanted to point it out, and I'm going to do it anyway. So there is a trig identity that involves things like this, and it goes like this. Sine of 3x plus 2x is sine of 3x cos of 2x plus cos of 3x sine of 2x. That's the sine addition formula for angles. And sine of 3x minus 2x will be sine of 3x cos 2x minus, and I know the minus goes with this one because it came out of that sine 2x. So, and if I go this one minus this one, I get sine of 5x minus sine of x is, they disappear, and I get two lots of cos of 3x sine of 2x. And so I get two cos of, nope, one cos of 3x sine of 2x is a half of sine of 5x minus a half of sine of x. Look, Fourier series. So I've got like that A0 is 0, and A1 is, all the A's are 0, and B1 is minus a half, and B5 is a half, and all the other B's are 0. That's a Fourier series. It's just that most of the coefficients are 0, so it doesn't go on forever. Yeah. And basically, Fourier series is an attempt to do this for any periodic function. I've got some ridiculous thing that's a sawtooth and a square and weird ass crap. As long as it's periodic, I can make an attempt to do this, but I'm just going to need infinitely many, usually, sines and coses. And it's very similar in vibe to Taylor series, which is like, well, it'd be super cool if my function was a polynomial. It's not, but I'll just do infinitely many x powers of x, right? So it'd be super cool if my function was a trig function. I know how those integrate and differentiate. That'd be awesome. So I'm just going to pretend it is and see what happens. So when you do Taylor series, the way that you figure out what the coefficients are is via derivatives. You say, all right, well, if I had a polynomial and I differentiated it enough times and subbed in 0, it would tell me the coefficient of x to the 7. We don't have a way of doing this via derivatives for trig functions. But what we do have is this. If you have two different numbers here, you'll always be able to turn it into cos of something, and sine of something, sine of something. And if you integrate this whole thing from 0 to 2 pi, you'll get 0. Because this one has period 2 pi, and sine, the integral of sine across its entire period is 0, because half of it's above and half of it's below. And sine of 5x is the same. It just runs 5 times as fast. So it'll just be above 5 times more often and below 5 times more often. So the integral's still 0. So what that means is that we can borrow this idea and be sure, and that's why I wanted to do this, so that I could make this point. We can be sure that cos of mx sine of nx, that integral is going to be like half of sine of m plus nx minus a half of sine of m minus nx dx. And if I go from 0 to 2 pi, I'll go 0. That's pretty cool. And I also know, now this will not work. No, that'll be fine. And I also know that based on trig identities, cos of mx, cos of nx, that one would appear in the cos addition formula. You'd have to have cos of this plus this and cos of this minus this. But I can never remember which way around everything is, but there'll be like a trig identity. There'll be cos thing and sine and cos thing, right, with a number in these spots. And that will come out to also 0, except in the very special and only case that these two numbers are the same. In which case you'll have cos of mx squared, and that will come out to 1, that will come out to this trig identity. There'll be an mx, and that'll be 2mx here. And so you won't get 0. You'll get half. And that's very interesting. So unless 0 to 2 pi of cos of mx, in which case you'll get that, according to the trig identity we did earlier. And that integral, this bit will come out to 0, but this will come out to a half high times 2 pi y, which is pi. Yep. That's okay. We're fine. That we can cope with that one. And the one with the double signs, it also comes out to 0, unless it's sine mx, and then it'll come out to also pi, I believe. Because it comes out to a half minus half of cos 2x. So sine, that'll be 0. Damn it, I should be more precise. In my head, I can just see the shape of the sine, and so I don't always, yeah. Unless it's that will also come out to pi. Okay, that's great. That's lovely. What this means is, because we know how the trig functions react when we multiply them by another trig function and integrate them from across the entire period, we can pretend all functions do that. So if you have a random function and you imagined it, imagine f of x to be these things. Then if I integrated f of x times cos x, all right? I'll have to deal with that, damn it. But this one will come out to pi. And this one will come out to 0, because cos 2x cos x, when I integrate it from 0 to 2 pi, gives me 0. And these all come out to 0. And so I'm just going to get out with a1 times pi, a2 times 0, b1 times 0 plus b2 times 0. This one will come out to, now I just need that one, damn it. We will be fine. So just at this point here, I just say, oops, I forgot. I need to multiply the number 1 by this. Oh, also 0. Yay, that makes sense. Cool. That's great. I'm very happy about that. And so this will also be 0. And so what you get is that 0 to pi f of x cos x dx is what a1 is. And I just have to divide by pi. Yeah. That is why the Fourier series coefficients turn out the way they do, why all of their formulas for what a1 is or a2 or whatever are based on an integral. Because instead of us using derivatives to figure out what the coefficients are, we've used the way that they interact with integrals instead. Yeah. Thoughts at this time or questions?
Minus 5 to 5, that is a prime.
Yeah, they go from minus pi to plus pi traditionally, don't they? Sorry, that's me being thinking on my feet. Yes, that it just has to be an entire period. So if the domain of f of x was less than the period of a sine thing that you want, that's okay. We can fix that. We can fix that. Just give me a second. So what if f of x is sorry, I should just answer I'm happy to sacrifice the whole piece of paper for that. Note and use integral from minus pi to pi of f of x cos mx or whatever it is. Because as long as you use an entire period, it'll be okay. Okay. In fact, you can even use the integral if your function f of x is even. You can use it from 0 to pi as well, and just times it by 2, because then that's the same thing. I think an even function times an even function is an even function. Yes, that's right. Even times even is even. Even times odd is odd, and odd times odd is even. Okay, right. So, and that's the one that people traditionally use instead. So what if f of x isn't 2 pi? That's a great question. That's okay. We'll just adjust the period of all the sines and coses. So we'll use instead cos of some multiple of, but what if it's 2L instead? That's tradition, I think. Well, when you replace x with x times pi, it divides the period by pi. Because replacing x with x times anything always does the opposite to the x-axis, to all horizontal distances. And so I'll replace x with x times pi. And when I divide it by L, that will multiply the period by L. And so this function has period 2L instead. Or at least, it will fit a whole number of periods in the space of 2L. And sine of m times pi on L. Instead. And what that means is that your integral won't be pi anymore, because if you do the integral across a whole period, of the one with its squared, right? So where'd that squared one go? This one here, it won't be it won't be a half times 2 pi, it'll be a half times 2L instead. And so that integral will come out to L instead of pi. And also the integral from 0 to from minus L to plus L, because that's now our tradition of cos of m pi on Lx squared dx will be minus L to plus L half plus a half of cos of 2m pi L on Lx dx, which will come out to a half wide and 2L high, sorry, half high and 2L wide, which is L this time. And so what will happen is that you'll get a m is 1 on L instead of 1 on pi. And I know they write it as m pi x on L, but that's not how I'm thinking about it today. You can write it that way if you want, but this is how I'm thinking about it to make sense of what's happening there. And so what if f of x isn't even periodic? That's okay. You just pretend it's periodic outside the zone that it's looking at. That's okay. Just pretend it is outside minus L to L. They call that a periodic extension. Well, L is normally chosen by the situation. So it'd be like, oh, it's the temperature of a metal bar that's 1 meter long. L is 1. Right, so yeah, you just, yeah. Usually L is chosen by the physical situation that the differential equation is. And so you will always be told the L or be given a letter for it because it won't, because that's what happens. Yeah. And actually, even better, what if it doesn't even go from minus L to L and goes from 0 to L? That's okay. Just pretend it's periodic outside minus L to L, and then pretend it's odd or even in the other half, and then you'll be fine. Like they go on and on about periodic extensions in these courses, and it's something that the lecturer wants you to know how to do. But no one really cares, right? Because you don't look at the function outside the zone that it's defined anyway. The point is you can't extrapolate. Because when you extrapolate outside that zone, you are automatically pretending that it's odd or even and periodic out there. And so you just don't extrapolate. That's the idea, because you are pretending. And that's a really good, to me, it's one of the cleverest little bits of maths. It's like, oh, no, I've got a function and it's just like something ridiculous. That's great. And I'm going, okay, and I'm just going to make a Fourier series for just this bit. But what that means is if I did a Fourier, e.g., Fourier cosine series for this. So technically, I can do whatever I want here, and I don't really care what I do here. But since it is periodic, and since it's made of causes, it must be even. And so there's a secret function out here. So that means I've turned it into an even function because I've used causes. And I've also turned it into a periodic function. As well. Yeah. And so if I extrapolated my answers beyond this zone, that's what would be happening. But I'm not going to because I don't care. Right? Because my problem only exists in this zone because it's like a bar or a time stops at that point or whatever. Right, so yeah. So anyway, questions or thoughts on that point? Okay. In this bit here or this bit here? Right, that's cool. Okay, so I'm just going to do it with cos x first. So if I have cos x, that's a full period of cos x there. And then it does that again. And it takes 2 pi to get an entire period of cos. But if I have just, for example, cos of 2x, that happens twice as fast. I will write that one in green. Have I done that right? Yes. Right? Happens twice as fast. So what that means is this one had period 2 pi, and this one had period pi. So replacing x with 2x, divided the period by 2. Is that okay? So what that means is cos of pi x will have period 2. Because replacing x with pi x divides the period by pi. And cos of pi x divided by L will multiply the period by L. And so now this function has period 2L, just like my original f of x did. And if I do that to all of them, including with the m there, then it will make all the periods 2L, or at least, there will be a whole number of periods fitting into that space. Is that better? Cool. So there's a lot happening in Fourier series. They do kind of mention it very blithely. It's like, oh, I can just use this integral thing, do it. But the reason why the integrals are the way they are is because of how we understand cos and sine work. And that behavior of how cos and sine work is what we call being orthogonal for functions. So if you pick, like there are many ways to do that integral, you choose a different zone. But if you pick a particular domain, and when you integrate the product of the functions across that domain, you get 0, then you call those functions orthogonal. And the fact that most of these functions, when you multiply them by each other, if we get any 2 of these functions in this list here and multiply them by each other and do the integral from 0 across the whole period, you will get 0 as the answer. And so they're all orthogonal to each other, which means that when you multiply this by any one of them and integrate, all the other bits will disappear except one of them. And that's why we care about functions like that. It is technically possible to find other collections of functions that are also orthogonal, and we can make fancy Fourier series that aren't trig Fourier series, but are something else. So they do it with I can't remember what they're called, the ones that are the solutions to one of the differential equations. The J's and the Y's. Sorry, Bessel functions. Yes. The Bessel functions for different news are orthogonal. And so you can actually make Fourier series out of Bessel functions if you want. And the reason you would do such a thing is if, sorry, Bessel functions. Oh man, probably. I just know that fact about them. Maybe. I wouldn't mind talking about Frobenius's method. But okay. So, how do we think about the Fourier series thing? So I do want to make one final point about Fourier series, is if your function is already written as a combination of sines and causes, it's already a Fourier series. And you don't have to do any integrals to find its coefficients. You just look at them and go, they're the coefficients. They're right there already. And so there is a moment when you do PDEs where you have something like not dx. You have something like this, right? Where you get something like that. And then you were separately told at an earlier point that f of x is like 5 cos of 3x minus cos of 8x or something stupid. This is a Fourier series, and this is a Fourier series. So you can just match up the coefficients and go, oh, right, cool, cool, cool. The coefficient of cos of 3x on this side is a3 minus 3 squared on, the minus would be pointless, wouldn't it? A3, 3 squared on 3 on this side, and on this side it's 5, and so therefore A3 is 5 on 3. Yeah. And then the coefficient of cos of 8x is A8 minus 8, A8 squared on 3, and it's minus 1, and so therefore A8 is minus 3 on 64. And that's it. Like, it tells you the coefficients. This is not exactly how it looks, because this is normally like fx0 or something, like there's a t in there somewhere and you've made the t go away by subbing in 0. But that's the idea behind it. You don't have to do any integrals or anything because it's right there. If, on the other hand, you were told that f of x was equal to x and it wasn't already a Fourier series, then you would have to find its Fourier series. So all other a_n's are 0, right? But if it was f of x equals x, not Fourier series, yet, so you have to make it into one, and therefore do all the integral things to figure out what its Fourier series is. Right. I think that'll do for now. We can talk more about it later. I personally won't be in the Maths Learning Centre in the mornings on Monday and Tuesday, because I'll be doing revision seminars. But if you want, there's lots of other people who know about these things. If you want to talk specifically to me, that'll be Wednesday to Friday. Okay. Last thing, Frobenius. Since 2 different people asked me about it, I think it's probably worth talking about it. So Frobenius's method is designed for calculating, is a power series sort of method, designed for functions with differential equations with polynomial coefficients. Officially, it can work for others probably, but I've never seen it, and it's really hard. So if you have something like this, a polynomial in x here, a polynomial in x here, a polynomial in x here equals 0, that is the situation in which you use Frobenius's method. Also the situation in which you use ordinary power series methods. Also the situation in which you use, I think it's called Euler-Cauchy. Yeah. All right. but Frobenius's is the most general version. And Frobenius's method is designed to work in situations when you put it in standard form and divide by this, that one is 0 at 0. Yeah. So it's designed to be that when you put it in this form, yeah, I should just call them P and Q or something. Like you get it to this point. You know, divide by this, and you get to here. It's designed for when one or both of these is undefined, when x is 0. I say undefined, but the official word is not analytic. Yeah. And it is specifically x equals 0. Because if it was defined when x is 0, you would have used an ordinary power series. That would have been fine. As opposed to Frobenius's method, which is a spicy power series. So, yeah. And also, Frobenius's method will also not work sometimes even in this situation. So you need to, not being analytic when x is 0 means that x equals 0 is a singular point. That's what it means. That's what we call it in official words. But not all singular points are made equal. It needs to be a regular singular point, as opposed to an, I guess, irregular. I don't know. Yes, it has to be regular for Frobenius to work. And ultimately, all that means is that if you multiply this one by x squared and this one by x, then you remove the bad bit of the polynomial of the denominator. Or is it this one by x squared and this one by x? X there and x squared there, yeah. The way I remember that is that this one's got 2, so that would be like 0, 1, 2, like the opposite way around. And they're the powers of x you have to multiply by to make it work. So it has to be regular, and regular means that x times px and x squared times qx are analytic. So all that means is that your denominator just can't be more than x, power of x here and power of x squared here. And what that means is in the original thing with the polynomial here, you can't have anything higher than x squared there, or it won't work. That's basically it. But you're supposed to divide them out and go, aha, look, if I divide out by that thing and then multiply by x squared here and x here, it turns out to be analytic, and it's correct. So ultimately, Frobenius's method is specifically designed for things with an x or an x squared in this spot. That's what they're for. It's for. And one of the classic places when that happens is in Bessel's differential equation, which is why Bessel functions are mentioned after this. So Bessel's differential equation has an x squared in this spot, if I'm right. Yes? Yeah, look at that. It's great. So basically, Frobenius's method is designed specifically for when there's an x squared here. If it was x squared minus 1, not a problem. We wouldn't use Frobenius. We'd use a plain old ordinary power series. The difference between them is that Frobenius's method has that plus r. Okay, So what you do with Frobenius's method is you put it back in this format. That's the important thing. Frobenius's method cannot be done from here. It's too hard. You have to put it back in this format to do it. And Frobenius's method is designed. You go like this. You suppose that y is do they use m traditionally in this course or n? That is the tradition, but it works just as well to write it like this. And it's totally okay not to write this one. What is? But the difference between it is that without the x to the r, that's an ordinary power series. And if you didn't have an x or an x squared next to that y double dashed, you would just not use the r at all. And so in the ordinary power series thing, like we kind of differentiate it. This is a classic Taylor series vibe where you go, well, I'm just going to assume my function is an infinite polynomial, and I'm just going to differentiate it until I figure out what the coefficients are, and that'd be great. That's how Taylor series works. But ultimately, our goal is to figure out what all the A's are. Find all the AMs, and we are also going to have to find R. So the M's, they're known. The M's are the numbers from 0 to infinity. They're perfectly good numbers. I don't need to find out what the M's are. I do need to find out what the AMs are. There is a list of coefficients, and I don't know what they are. I'm going to need them all if I'm going to know what Y is. But if I'm really lucky, and especially if my X's in my original problem are less than 1, which they would be if you non-dimensionalize them, which is, I think, the point of non-dimensionalizing. All your variables end up being less than 1. And so that means that the higher powers don't matter. So I only really need to find the first few. So it's okay to set up a system where you don't find all of the AMs simultaneously, and you just find the first one and find a way of figuring out the ones later. And so instead of finding all the AMs, what we're actually going to do is find like a way to calculate later AMs from earlier ones. And that'll be okay because most of the applications we need, the x's are small numbers anyway, and so the later coefficients don't matter. And this thing, finding a way to calculate later AMs from earlier ones, is what the recurrence relation is. That's the idea. We have now two goals, find R and find a recurrence relation. If we're lucky, things will turn out nicely. And actually, this is the goal, but the ultimate real goal is actually just to find two solutions to your original differential equation. That's the real goal, because then you can go, C1 times this solution plus C2 times this solution, and now that's all the solutions. Other than the spicy ones, but that's that's the general solution. But the real goal find two solutions for y. Like that's the real goal that we're keeping in the back of our mind. So at some point, we're probably just going to choose A0 to be like 1 or something, and then we'll get an answer. Right. Is that okay, me saying that? Like most of the things in this course are about trying to find two solutions to your homogeneous differential equation so that you can go C1 of this one plus C2 of this one. So when we get to Bessel's functions, they are solutions to a specific kind of equation. So that you can do the C1 whatever with them. Okay, that's Frobenius's method. And the way that we're going to figure out what the A's are is to go, well, if this is the solution and it has to satisfy this equation, we'll differentiate and sub it in and see what happens. But we're going to have to do, the plan is this. Differentiate twice, sub them in. What that will do is create like a little collection of infinite series. And we're going to have to somehow combine those series together. And the first step is we're going to combine the series by making their exponents match up so that we can match up the exponents of x. So match up powers of x. And then what we're going to do is going to set all the coefficients to 0. Because it's equal to 0. And the Taylor series for 0 is 0 plus 0x plus 0x squared plus 0x cubed. So you can just set all the coefficients to 0. That's the plan. When you set the coefficient to 0, the very earliest coefficient, the one that goes with x to the power of r plus 0, is the one that will tell you what r is. So the earliest coefficient will tell you r. And then the others give the recurrence relation. Yeah. So setting the earliest coefficient equal to 0 is called the indicial equation. I don't know why. I think it's because it indicates things. But it would be nice if they just call it the indicator equation. But whatever. They can't call it a characteristic equation because they've used that already. Okay, that's the plan. And once you've found r, then you can do a different recurrence for r. When you do an ordinary power series, that step's not there. But it is worth noting that there may be an extra bit of spice where some of the other coefficients will actually tell you the values of a whatever, straight up without a recurrence relation at all. So sometimes you get freebie ANs from the other coefficients. It happens sometimes. And they tell you that if like A1 is 0 or something. That's happens. So let's do an example. We've got a little bit of time to get going on an example. The made-up thing, I put polynomials in all these spots. I put an x squared there because that's the tradition that this thing is designed for. And so if I do divide by x squared, oh no. That's not going to work, is it? I'll just leave it what I said earlier. Right. That's fine. No, sorry. You can see me thinking about this and going, oh, if I divide by x squared, I need that this one, when I've finished, when I times by x, it removes the denominator. And this one, when I times by x squared, it removes the denominator. That's yeah. So standard form. Like that. And so I have that this one, x times 3 on x is x, which is analytic. And this one, x plus 1 on x squared times x squared. Damn it, I'm sorry, I put it not in the right order again. Here we go. Is x plus 1 analytic. but both of these are not analytic. So that's a problem. So not analytic at x equals 0. So what we have is that x equals 0 is a singular point because it's not analytic when x is 0 with these original coefficients. And it is a regular singular point because when I multiply them by the matching x's, it works. Okay. So Frobenius's method will work. Okay. So I am going to suppose that y is m equals 0 to infinity a m x to the m plus r. For some r which may or may not be a whole number. So you're always supposed to do that checky bit before you do it. Because if you don't, it might then you may be in a situation where Frobenius's method will just fail spectacularly. And so yeah. Also because there'll be a mark for it. Let's just be mercenary about it. Okay. So y dashed. So this first bit is the same no matter what. I differentiate, multiply by the current exponent, make the exponent down by 1, and y double dashed. Okay. Yep. Thanks for mentioning that. So in the power series version, they often start this at 1 after they've done the derivative. That's what you're saying? Right. Just a little interlude. If there wasn't an R there, then when you do this, then when m is 0, right? This whole thing is 0. And so the 0th term is 0, and so it doesn't matter if you have it or not. Yeah.
So you could still have it.
You could still have it, and it would be okay. But philosophically, it's not really that it's just, there isn't, when you differentiate something, you don't magically create x to the minus 1s. Like you can't create an x to the minus 1 by differentiating a polynomial because you'd have to start with an ln. So from the perspective of, so there's two perspectives. One perspective is that if m equals 0, there's no 0th term because we times by 0, right? And so you could just as easily start at m equals 1 and it wouldn't make a difference. But the other reason is that when you differentiate this thing, literally this first term just vanishes entirely. And that's the main reason why we do it. Okay, but if it's not necessarily going to disappear because we don't know what R is. R could be 7, in which case the first one is going to be a 7 times whatever. It's still going to be there. So it's not going to disappear. R could be like 2/3, and then it's just going to be stupid. So that's the reason why. And the other reason why is totally, it doesn't really matter if you leave it in or not, because it should all work out anyway. But it sometimes makes people feel uncomfortable if you leave it in when it really should, by rights shouldn't even exist. And so, yeah, the question is, I think it's one of philosophy. It's like, does it really, it doesn't really exist an x, this one, leaving it in kind of implies that there's an x to the minus 1 term, but it really isn't. But in this one, there might be an x to the minus 1 term. That's totally possible. Yeah. So might not be 0 when m is 0. So we have to leave it in. Okay, good. In general, we are assuming R is not 0. Though R is 0 sometimes comes out to be one of the solutions anyway. But even if R was 0, it would still be okay to leave this in here. Because it's going to be times by 0 anyway, so it doesn't really matter whether there's an x to the minus 1. It's all fine. And to be honest, when a lot of these things were invented, people just weren't that finicky about it. So it's just people are a lot more finicky about calculus than they were when calculus was invented. Oh no, I've mixed my Frobenius and my Fourier series together. Okay. I mean, that's what real analysis is for. So that we can, those little worries we have about calculus, weird, dodgy things happening in weird, dodgy situations in calculus, that's what real analysis is for. But in differential equations, we don't have to worry about it that often. It's fine. Please don't say that to your lecturer. But I feel like that's probably sounds, no, having met Elizabeth and talked to her about it, I think she feels similarly. Okay, so you've done your derivatives. And now what we have to do is we have to sub them into the differential equation. So my dE was x squared y double dashed and 3xy dashed and x plus 1y equals 0. And so I'm just going to be a little, I'm going to do this. Just expand that one out. And any of other ones that had more than one part, I would expand them out. It would make me a little easier to do. So here we go. X squared times y double dashed is this one here times x squared. And if I times by x squared, that'll make this exponent go up by 2. So it will be exactly the same. I'm just going to put a note here. Exponent plus 2 since we times by x squared. That's why it went up from minus 2 up to 0. And the 3x times y double dashed. The y double dashed was this. But then I times by 3 and I times by x. And so that went up as well. And the x times y y was just am x to the m plus r. That's going to go up by 1 because I times by x. And the 1 times y is whatever it was originally. Now, I have done the bit where I subbed it in. I've done that part. That's great. I've done the subbing in. And I'm just going to make the point here that the total of all of these things is 0. When I add all these 4 things together, they should all come out to 0. That's what subbing in means. But I'm going to have a really hard time adding this one to the others because the exponents don't match. And so I have to shift the indices of this one so that the indexes match, the powers match, exponents match. And then I'll be able to add them together, which is what I have to do. I have to figure out the total. Okay. So I would like this to be m plus r instead of m plus r plus 1, which means I've removed 1, subtracted 1 from here So I'm going to subtract 1 from all of the m's in this bit here. And I'm going to add 1 to all of the m's here. And that will cancel out the change that I've made. And just to check that it's all working out correctly, if m is 0 here, I get a0 x to the r plus 1. And if m is 1 here, I get a0 x to the 1 plus r. They are the same. And if m is 1 here, I get a1 x to the r plus 2. And when m is 2 here, I get a1 x to the r plus 2. It's the same list of things. I've just made them by subbing in different numbers. So I've subtracted 1 from these and added 1 here. And now I know that when I add all of these together, it should come out to 0. Right. And so what I'm going to do is, you could, if you really wanted, write sum m equals whatever, right? And put a big sum there. Unfortunately, this sum, we've fixed one problem, but created another one. So we fixed the problem of the exponents not matching, and now we've created the problem that the starting points don't match anymore. So we're going to have to deal with the starting points not matching as well. And what some people do is that they peel off the first term of all of these and write it separately, and then add the sums together. I just personally write down the coefficients of each individual m. So the coefficients or the values of m. So when m is 0, I've got a from this one, a0, 0 plus r, 0 plus r minus 1. That's the coefficient of x to the 0 plus r. That's what happens when I sub in m equals 0. I get 0 plus r here in all of these spots, and I get that. So that's my first thing. When m is 0, the coefficient of x 0 to the 0 plus r, and I'll get a0, 0 plus r, 0 plus r minus 1. That's the coefficient from this one. And the coefficient from this one is 3a0, 0 plus r. That's the coefficient from this one. This one doesn't have m equals 0. So I'm not going to use it. And this one is just a0. So didn't use x, y, since there's no m equals 0 there. That's just my note, just to make sure that I know what I did. And this thing is supposed to come out to 0, because all the coefficients have to come out to 0. Okay. And a0 is not 0. If it was, I would have made my r1 higher and started everything a little later. That's basically it. So a0 is not 0. And so I can divide by that, and I've got r times r minus 1 plus 3r plus 1 is 0. What's that? This is the indicial equation. And it always comes from the earliest m that appears anywhere in your sums, which is usually m equals 0. But sometimes if you've shifted all of them, then sometimes you get m equals minus 1. So, yeah. So there are situations where the coefficients are such that most of them have an m plus r minus 1, and one of them has just an m plus r, and it's much easier to just shift the one that's different forward by 1, which puts the m back by 1, and you get m equals minus 1 as the earliest one. So you just have to use whatever the earliest m that appears in any of the sums is, and that's the one that will be the indicial equation. But that's okay, you're just being systematic anyway. What's the first m? It's m equals minus 1. This is the initial equation, and whatever the solutions to that are the values of R. I am not a fan of this equation, but I did it to myself. Oh, yay! That's just glorious. Oh, I did not expect that at all. But, okay. I have such good instincts, apparently. So I only got one solution. Sometimes you get two. It's quite common for there to be two different R's. If those two different R's are different by a natural by an integer, then you can only use one of them. If they're not different by an integer, if I had like 1 and 2/3, then traditionally you would actually do the next bit separately, once for R equals 1, once for R equals 2/3. So you're supposed to run through both values of R, but I've only got one of them, so I'm a little afraid, but that's okay. Sorry? That's okay. That's all right. You just use reduction of order to figure out the other one. The U times the one I've already got, and then reduction. Oh, there's a thing with an ln or something. Yeah. Yeah. There's a thing with an ln in it. You can look it up. Or use reduction of order, which is what caused that thing to happen. So, yeah. Okay, so R equals -1 is what we've got. And so now, from now on, everything else can be done with knowing what the value of R is. No, usually there's two. I've not the slightest clue what to do if you ended up with a complex solution, but that's probably got an answer too. In your notes? No, maybe that just never happens. Sorry? Maybe that's why we have to have a regular singular point. Oh, okay. Cool. I guess you'd get some sines and causes or something. Fabulous. I guess there'd probably be some sines and causes along the way. No, I don't believe it. No one would want to mark it. So that'd just be causing themselves pain. Okay. So now that we know what R is, we can sub that in to the coefficients in a minute, but I'm just going to do it with R first and then sub it in after because that's usually easier. So at this point, I just need to check the values of M that are included. This one has an M equals 1, this one has an M equals 1, this one has an M equals 1, this one has an M equals 1. They've all got M equals 1, so everything after this I can just do in terms of M. But I will say, if this had been an x squared y here, then this would have been an M equals 2, and I would have had to do a whole separate piece of working just for M equals 1. Because it's another M that doesn't appear in all of the solution, all of the sums. So any M that only appears in some of the series, you have to do it separately. Just want to say that. So I really should have put an x squared for my example here because that would have really rammed that point home, but that's okay. So M is greater than or equal to 1. So here's in all the sums. Is it? Cool, that's fine. M is greater than or equal to 1 appears in all the sums. And so therefore I can just add all my sums together. And so the coefficient of x to the m plus r is m plus r minus 1 and 3am m plus r and am minus 1 and am. Okay, and that is supposed to be 0. And what this tells me is how to figure out the later m's in terms of the earlier m's. And so what I should do is write an equation that has the latest m that appears here on the left and everything else on the right. So look here, there's am, and that is later than m minus 1. And so I'm going to get to here, am equals everything else. That's the goal. And this thing is called the recurrence relation. That's the goal. I must stop in 5 minutes now. Well, I guess I can move all this over. Maybe I'll factorize out the am first. No, this sucks. No, one step at a time, David, or you'll just get a mistake. Okay, so am minus 1 is this. Times damn it, am. Wait, David, it's just going to be a division, you stupid person. Please don't normalize calling yourself stupid. It's bad for you. We need am equals. I even wrote myself the goal on the paper, and I didn't read it. There you go. There's our recurrence relation. And if you look at it, this denominator is going to get bigger and bigger and bigger. So now that we actually know what R is, am is minus am minus 1 over m minus 1, m minus 2 plus 3 m minus 1 plus 1. And I could probably do some working on that to get something nicer. Oh, I can. If I factorize out the m minus 1 out of these two, I'm going to be left with an m minus 2 plus 3, which is m plus 1. So cool. And that's m squared over m squared. That's amazing. Wow. I did have good instincts today. Yeah. And so this is telling me that A1 is minus A0 over 1 squared. Is minus A0. And A2 is minus A1 over 2 squared, which is minus A0 over 4, which is A0 over 4. Yep. And so each one of them will be able to be written as a multiple of A0. And A3 will be minus A2 over 3 squared, which is minus A0 over 4 over 9, which is minus A0 over 36. And so it'll get, this is going to get more and more extreme. Yeah, and so look at that. And so we're going to sub all of that into the original thing. And the original thing was, just go to all the way back to the beginning here. Here. So all of that into the original. So we've got that y is the sum of m equals 0 am x to the m minus 1, because that's what R is. I'm just going to do this properly. And so when we get m equals 0, we've got a0 x to the minus 1, and a1 x to the 0, and a2 x1, and a3 x squared, and so on. and we have just figured out what the first several ones are. So we have a0 x to the minus 1 plus, so minus a0 times x to the 0 plus a0 on 4x minus a0 on 36x squared, like that. And so that's our solution. And look at it, it is a multiple of that. And that's as good as we're probably going to get. And so what we have found is that really any multiple, we're going to be taking this solution and finding another solution and multiplying it by stuff anyway. So it's this that's the solution we're interested in. Yeah, this is one of the two linearly independent solutions I'm looking for. Unfortunately, the other one will have that ln thing in it. So look it up in the in the notes. Or you can use well, you can philosophically imagine that reduction of order will do the trick. Yeah. Okay, that'll do. Thank you for being here, and I hope that was helpful. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Yeah.